But I'm going to talk about trying to quantify the global economic value of climate science. I'm Bruce Wielicki, a climate scientist from NASA Langley Research Center. My partner in this is Roger Cook. He's the lead author on IPCC AR5, Working Group 3, Chapter 2, and from Resources for the Future in Delft University. An outline, science is really an economic investment by the public. A lot of us like to think they just pay us to do this great stuff for fun, for free, but actually they expect things to come out of it. Another point is we will be managing the Earth's climate until civilization moves elsewhere. That's a really long time. We've entered the Anthropocene. We're going to have to do it into the future indefinitely. We have no current climate observing system, nor do we have a plan to create one. Should we invest in one? Is it worth it? And in that sense, what is the economic value of an advanced climate observing system? We currently just use weather, research, whatever we can cobble together, and that limits, in many cases, what we can do. So I'm going to show you an initial framework that suggests actually the answer is it's really big. So here's kind of the climate change building under construction. So science is down the bottom, then the economy, then society, law, and governance. We've had a lot of talks today in kind of an interdisciplinary sense of merging climate science up here with trying to get the law and governance and public to understand it. We've also had talks about how to link climate science information into societal decisions. I'm going to talk how we might link science into understanding of its economic value to society. So what is that economic value? I'll first argue that we have a few traceable estimates of the economic value of weather prediction, things like better hurricane tracks or better storm predictions for floods. Climate scientists will often say from their research, this will inform societal decisions with trillion-dollar impacts. What justification do we have for that? What's our traceability? What's our ability to prove that? So if we wanted to quantify it, we actually would have to admit, okay, climate change science value mainly exists decades into the future. That value has to be treated as a risk-benefit economic analysis, basically. And a rigorous analysis has to take into account the uncertainties in climate science, economic impacts, and policy altogether. But if we could get science value and economic frameworks together, we potentially have a new way to talk about strategic planning and what is worth investing in Earth observing systems, as well as the other parts of science, the modeling we do, the in situ observations, as well as communicating the importance of what we do and what its value to society is. So how did we get there? What pushed us to this economic view? Part of it was one of the science things I lead at Langley is a new mission called Clario, which was out of the Decadal Survey. It was a mission to increase by a factor of 5 or 10 the accuracy we have in our instruments across the entire solar spectrum and the infrared spectrum. That's where most of our measurements actually come. That includes temperature, water vapor, clouds, radiation budget, vegetation on the planet, snow cover. And the idea was basically to take the last 10 or 20 years of NIST and other metrology lab advances in calibration, launch them into orbit, make an instrument designed not to measure the whole Earth, instead to calibrate other instruments and basically become a standard that allows you to get back to international standards for 30 to 40 Earth sensors up in LEO and GEO orbits. That means low Earth orbit and geostationary. And do that in such a way that they were accurate enough that even if there were gaps in the record, you didn't lose the accuracy of decadal climate change, which currently we cannot do. But in doing that, we had to come up with a logic for what that accuracy had to be. What's the requirement for that? What is the accuracy we really needed to get to? So this is just an example to show you how many satellites are involved. If we look at GEO and LEO that you might want to calibrate in the solar and infrared, here in circle is all the ones that have instruments that would be relevant to that. And here's what we argued about literally for a year with this science team of 30 to 40 scientists. How do we come up with a quantitative metric of how accurate you need to be for decadal change observations to be able to survive things like gaps in your records and be traceable to international standards at accuracy? And what we came up with is the following. Here's magnitude and observable trend in anthropogenic change that you want to measure. Here's the length of the observed trend at the time you have to measure it. If you're down here at 5 to 10 years, there's a lot of noise, even for a perfect observing system. By this I mean perfectly accurate observations everywhere on the globe all the time. What are they limited by? Something called natural variability, things like El Nino, things that are nonlinear coupled things that are noise in the climate system. So what happens is down these short time scales, you've got a lot of noise. This is why short, as we've heard discussed this week, short-term trends in temperature don't really mean much. It's the longer ones that start to get you to accurate identification of anthropogenic change in the system. And second, let's say we wanted to understand something that's really critical, like climate sensitivity. You just heard that talked about from Mike. In the IPCC, we currently have a climate sensitivity uncertainty, and think of climate sensitivity as the volume dial in the climate system. You put CO2 in the atmosphere, the amount of warming in the globe that comes out is climate sensitivity. That number is uncertain to a factor of 4 at 90% confidence. So if you want high confidence, that's the kind of uncertainty we're talking about. Now, when I've worked with the economist in the last year, what the economic impact models show, and this comes out of the U.S. Social Cost of Carbon memo, this is the Bible for economic impacts of climate change. The answer is it's related by squaring the amount of global warming we get. So if you have an uncertainty of a factor of 4 in climate sensitivity and warming, you have an uncertainty of a factor of 16 in economic impacts. That's a real challenge for society to deal with in terms of planning. So if you want to understand climate sensitivity, one of the things you have to understand is the biggest uncertainty in climate sensitivity is cloud feedback. In particular, low clouds. If you decrease the amount of low clouds as you warm the planet, you get more sunlight absorbed by the planet, and it amplifies the amount of warming. It's positive feedback. It's actually present in most climate models, but in very varying amounts. So that's actually changing the sensitivity of those climate models. And what you can see is that depending on the magnitude of that feedback, if it's large, you'll have high climate sensitivity and large economic impacts. If it's lower, you'll have moderate climate sensitivity and lower economic impacts. And you can see with this perfect observing system, the bigger signal you'd get from a larger cloud feedback you would see sooner, the smaller one you would have to see later and go further out in time. So this kind of represented an intellectual framework for understanding what you need. And here's our current observing system. Here in yellow are kind of our imaging instruments like MODIS and VIIRS. These are the instruments we use to kind of get the blue marble picture you see and everything. And then here's our most accurate current sensor of the radiation budget of the planet, the Ceres instruments. And you can see there's a big gap between a perfect observing system and where they are. And here's the kind of level in blue that we could get to with the kind of factor of 5 or 10 accuracy improvement I'm talking about. So the real key this kind of picture presents you is there's a potential of 15 to 20-year advance in the accuracy and confidence of climate information if we have more accurate observations. Now, you still have to do all the climate modeling to convince yourself of what you know and don't know. You still have to do the in situ observations. You can't do this just with satellites. But this is basically the thing that was the aha moment for Roger Cook when he saw this, because he said, if you can give me a time scale to advance climate knowledge, I can tell you what that's worth economically to the world. So what we did then was combine this new Clario climate accuracy framework. By the way, that's coming out in a paper in BAMS this fall. It's been accepted for publication. We added the interagency social cost of carbon, which is the U.S.'s standard for what economic impacts are versus the amount of warming you get. We added an integrated economic model. This is the kind of thing that they use in the interagency social cost of carbon. In particular, we use the DICE one if you want to go look it up. And then we put those together to get a global value of improved climate information. So how do we do that? Here's kind of a simple schematic to explain it. You start with business as usual emissions, the kind of path we're on now. Climate sensitivity will then amplify that into warming and all the other impacts you get, sea level rise and everything else at scale with warming. That gives you the climate change that then turns into the economic impacts. However, society is sitting here trying to make their decision by looking through a couple of fuzzy lenses at what's really going on with climate change. So if you want to think about this as anthropogenic climate change, the first fuzzy lens we have is the natural variability I talked about. We only have one planet. We can't ensemble planets the way we can climate models. The second fuzzy lens we have is an inaccurate observing system. Both of those are confusing and confounding our ability to see straight to climate change anthropogenically, but we have to get there to get to a societal decision. Once we get a societal decision, we start heading toward reduced emissions. That, through climate sensitivity, goes to reduce climate change, and in these economic assessment models, that leads you to reduced economic impacts. And the value of the climate science information, in a sense, is the difference between these economic impacts as a function of when society can make that decision. So if you think about it, if I can move society's knowledge of climate change and the confidence in it forward, however it makes that decision, that time frame I can move it forward becomes the critical thing to understand what the value of climate science to society is. So we looked at that. We took a bunch of scenarios. This is just an example of one. Here's a 3 degrees C climate sensitivity for double CO2. This is world damages as percent of GDP from things like sea level rise, food shortages, health, and extreme weather. You can see in the black curve what you get if you do nothing and you just use business as usual. And by the way, by the time later in this century, you get to 3 or 4% damages of GDP per year. Remember, the recent economic crisis with the financial crisis we had was sort of 2 to 3% GDP effect. So you're literally at that level and then above it as you go out into this century. This is what the economic models show. And if you do some sort of a trigger with requiring high confidence, accurate measurements with our current observations, you might literally be way out here in 2065 before you act and then go on a new trajectory. If you're 20 years earlier, you're here, you move at a lower trajectory. It's this difference that you can actually look at as climate science value. And then you do have to do a discount rate. We're dealing in the economic world here. Discount rate means if you had invested in something else, society could have gotten benefit out of it. The typical value used in the interagency social cost of carbon is 3%. So we took all those and used them 3% per year to get them back to this present time frame. What that means, for example, is economic impacts out here in 2115 are actually discounted a factor of 10 when you use a 3% discount rate, but you go back 100 years in time. So we took account for that. That's really something the economists feel you have to do. They still argue about what discount rate you should use. So the other thing we did is we did varying discount rates, but we also did thousands of these economic simulations because we don't know what climate sensitivity is. So we took the full distribution from the IPCC from 1.7 to 7.1, ran these economic simulations over all those cases, and then got the value of an advanced climate observing system at roughly about $12 trillion to the world in net present value. That does all the discounting we just heard talked about. What would be the cost of an advanced climate observing system to the world? If you want to do a really rigorous one, you might be talking maybe $10 billion a year worldwide. For 30 years, such observations might cost you $2 to $250 billion in NPV, net present value. If you ratio that to this value, you're talking about basically getting back about $50 for every dollar you invest. So this is clearly something that has a powerful leveraging effect in where we go in society in the future. We also looked at what the sensitivity to our assumptions were. So we looked, for example, as we can change which emission path we switch once society makes a decision. In particular, our normal one was to go from business as usual to a DICE optimal kind of moderate emissions scenario. That's what I showed you before. We could also go to a Stern-like aggressive emissions scenario that drops slightly the economic value because you're getting rid of climate change impacts faster. We also looked at society waiting later with a higher temperature change trigger they wanted to use to trigger a societal decision. That moved the value up because you got then into bigger impacts. We also looked at what our current baseline assumed you launched some advanced system, and by that it means in situ, climate science, and satellites in 2030 and 2020. If you delayed by 10 years to 2030, your value drops from 11.7 to 9.1 trillion. Interestingly, then, you now have a metric of what the cost per year is. You literally lose 2.6 trillion for 10 years of loss. That's about 260 billion years of 260 billion per year of lost benefits. So we have this out in a paper that's being reviewed now, and it was accepted with minor revisions. We're finishing those up now. So any of you who want to get that, I can get you both of those papers. And so I think in the end, a modest investment down in this end has the potential to actually make some pretty sizable payoffs up in the economic end. Thanks.